How does a two-wheeled vehicle get us from point A to point B? Bicycles make this possible by combining simple machines into what is known as a system. The rider is only one and the sole biological element, crucial in establishing whether a system is living or not. For it to be considered a living system, it must fit into the following characteristics. So far, we've crossed 2 out of this checklist. The rider is an organism that has a hierarchy and is part of a hierarchy, and as we will see further, the bicycle mostly consists of abiotic parts.
Can you identify most of them? If you're having a hard time, you are not alone. In fact, the bicycle is a type of complex machine composed of varying parts that differ in function individually. So for simplicity, we will be focusing on these 8 main components, including the rider, which possesses the energy that the bicycle converts, and the one responsible for maintaining momentum and stability, the ground, responsible for preventing the bicycle from slipping by exerting a force called friction on the bicycle's front and rear wheels to work in backward and forward motion, the front and rear wheels that reduces drag through rolling friction, the pedal, which works with the rotational force of the rider's feet and turns the gears attached to the chain. The chain, a set of links, assists the pedal by turning another set of gear at the rear wheel. The handlebar is a type of lever which functions for steering and gliding. And lastly, the handbrake, also a type of lever, stops the motion of the bicycle through friction.
But how exactly do these parts affect each other? Generally, a bike efficiently converts the power of the rider into kinetic energy. To ride a bike, the rider places their feet and exerts energy from their leg muscles to push on the pedals. A chain connects the pedals to the back wheel, making it turn as the pedals are pushed. As the back wheel turns, force is applied on the ground and rotates the front wheel. The rotation of both wheels then drives the bicycle forward. In case you need to stop, the wheels are halted by hand brakes by way of friction, converting kinetic energy into thermal energy that has enough power to impede the wheel's revolution. A pair of rubber shoe clamps are applied to the rims of both wheels as the handbrakes are pressed at the handlebar. The handlebar has a lever that pivots the front wheel. Its inner part is used by the rider to glide, while the outer part is utilized to steer the bike towards the rider's destination.
Although these elements serve different tasks, they all work together to achieve one goal: transportation. Each part has a specific purpose and requires the presence of other parts in order for the bike to function effectively, such that without the pedals, the chain would stop working, the wheels would then stop turning, and the bike would malfunction and cease to function as intended.
As seen, many of the interactions between these elements were primarily governed by physical forces and were not biological in nature. With the last item on our list crossed off, we can say that the system is non-living.
In any case, a system depends crucially on interactions and other factors. Would the effect still persist in a variety of circumstances? In the event that you wrap the chain around the wheels instead of attaching it to the chain cocks, the bike would be harder to move. The effect would also be affected by the type of terrain traversed by the bike. Rougher surfaces would be difficult to ride on than smoother surfaces. Cycling on uphill terrain is also more challenging than on flat or downhill terrain. Another circumstance depends on the biotic element, the rider. The more skilled the rider is, the more efficient energy is inputted, making the system work better. As seen by these examples, the purpose and effect of a bike will vary depending on the arrangement of the elements, the environment in which the system operates, and the energy input. Thus, changing relationships usually change system behavior.
Generally, things in the objective world are linked to and influenced by one another, and everything is assembled to be a system. It may be mechanical, biological, or social, among other possibilities. Hence, models are critical in presenting complex systems and events in order to help us comprehend and gain knowledge about them. Complex systems may vary significantly in form and function, however, most share a fundamental underlying pattern. They consist of ensembles of interacting elements. Comprehension of these systems arises from learning not only the behavior of constituent entities, but also how they interact to establish the behavior of the whole.